Okay, so good afternoon, everybody. This is Paolo Pagano from the National Consortium of Telecommunications in Italy, and I'm the convener of this webinar. It will show the plans and the results coming from the Italian testbed of the project that is named AUTOPILOT. And the agenda today is the following. We have a very short webinar introduction by me with shown context and motivations. Then Lorenzo Pieri from AVR will introduce the testbed and the use cases. Then the 1M2M platform we use in the project will be shown by Telecom Italia. Paolo Scalambro will be the presenter. In turn, the vehicle features and IoT-assisted autonomous driving maneuvers will be described by the Fiat Research Center, FCA Group. Leandro Dorazio will be the presenter. And then finally, the description of onboard units, pothole detectors, smart traffic light, algorithms for pedestrian detection will be presented by Daniele Brevi from the Istituto Superiore Mario Boella in Turin. The final slot is for questions and answers. Okay, so the objective is to communicate to external public, of course, and then include external audience into the development of the project, and also to start a debate about automated driving. So the intended audience is that of having research stakeholders, industry stakeholders, institutions and authorities, and autopilot partners. This is not optimal because it's not in slideshow. Please forgive me about it. Okay, I will briefly introduce the technical motivations of the Autopilot project. Then I will discuss the situation in Italy that is moving from standard to normative. And then I will discuss the Italian pilot site scenario and the specifications of our pilot site. So far we have in this cartoon some sensors on board of our vehicles, and this is providing support for automated driving by detecting obstacles and information in a range of about 100 meters. If we move further, vehicular network can provide additional information. This is the so-called cooperative ITS scope. And if we go again out of the line of sight communication, we can retrieve information from the cloud. Actually, this is the idea of Autopilot, that the cloud is providing readings about the internet, about the situation as instantiated by the Internet of Things, and this will be retrieved by a common platform. Namely, in Italy, we are using the 1M2M standard. So this is the set of sites and applications that are considered in Autopilot. So we have the Finnish, the French, the Italian, the Korean, the Dutch, and the Spanish pilot site, and the Italian one, which will be described today by me and by our collaborators and colleagues in Italy, will be about the use of IoT for the autonomous driving in the context of highway and also for urban driving. So the scenario where we test all these functions coming from the IoT is that of the port of Livorno. Is a very, to say, interesting scenario because it's an industrial settlement. It's a multi-purpose port from the 16th century, and it is not the least of the European ports, as it will also host the European Seaport Conference in 2019. Apart from the port settlement, we also have a highway. It's a remarkable highway connecting Florence to Pisa. In the project, there will also be the traffic control center that features a DATEX2 node integrated in the National Motorways Information System. And also the traffic it's a very busy, actually, highway, because 40,000 vehicles per day with 20% share of heavy vehicles is something that ranks it among the topmost of the Italian scenario. And we will have HCG5 coverage of the highway in Autopilot. Last picture I want to show is that what we have discussed so far in research projects and in standardization activities now turns to be normative in Italy, as starting from a decree that has been published on April 18th, we are considering the use of autonomous driven vehicles in public roads. And this is possible only in smart roads, those featuring HCG5 connectivity, and upon the approval of by the Ministry of Transportation. That's it. So I would like to stop in here and give the floor to engineer Lorenzo Pieri from the highway company.
Thank you very much, Paolo. So yes, my screen should be viewable by now. Can you see my screen?
Yes, we can.
Great, perfect. So I'll start the introduction. Yes, perfect. Yeah, this should be it. Okay, so good evening, everyone. My name is Lorenzo Pieri, as presented by Paolo Pagano. I'm part of the AVR team, and we are following the highway and participating in the project for the Italian pilot site, along with the other partners that are involved. The first of which is CNIT for the telecommunications and FCA for the automated driving cars. There's also CRF actually. There's also Istituto Mario Boella, Continental team, and Thales for the security of the site. Paulo Pagano already described part of the site, so you may as well know that it's a highway composed of 100 kilometers both way roads, and the traffic is very dense. As stated, it's about 40,000 vehicles per day, with 20% being heavyweight traffic. So the testbed encompasses the area that goes from the port of Livorno to the Florence Livorno highway, and IoT devices are in fact deployed all along the roads in both ways, with the radius of the devices spanning throughout both sides of the roads. And these devices are both installed on the highway and the urban area. To test the devices, Jeep Renegades prototypes were used. AVR and CRFs are making possible for the presence of a few Jeep Renegades, and some of which, as I said, are connected, and two are automated drive-it cars. There is also a connected bicycle prototype, which is part of the project and is part of the Port of Livorno use case. And all of this is going to work and be shown in the Monica Port Monitoring Center to make sure that security is shown and is the #1 priority of this project. So to make sure that all devices are connected and work well together to establish a level of connection and information that is useful to the final user and to the other devices as well that are connected, in fact, to the shared space, which is the cloud in this case. So pretty much all information is transferred and seen by the traffic control center, which sits in Empoli, which is halfway through the highway. And there are two use cases. One is the highway pilot, and the other one is the urban driving. On the highway pilot, you can find the road hazard events, which are briefly announced by the IoT devices and should enable speed adaptation and lane change functions on the AD cars. On the connected cars, they should enable the pass-through of information to make it possible for faster decision by the user of the connected car. On the other hand, on the urban driving scenario, the vulnerable road user is detected at a traffic light intersection, and it should trigger a brake by the AD car and the knowing of this VRU on the connected car. So as to the scenario we just saw, there are two possible cases, but the big thing is about avoiding incidents and accidents in the real world environment, which in this case, as I already said, is about a highway with really large traffic numbers. And the most common events are pretty much roadworks, which is why that was chosen, and rainwater standings, because we are entering autumn. Like we entered autumn yesterday, and the rain is coming along with the winter, so we have to make sure that the final user is safe, and that is why the use case wants to make sure that these devices work correctly to pass through the information. And let's see the next slide. On the urban case, all information, as well as with the highway, is passed through the 1M2M cloud, which takes in and hands out information with known IoT protocols, which could be MQTT or even HTTP or sockets. Anyway, there is the chance for the cloud to make this information available readily and fast to the connected environment. And this way, in the urban use case, there is a way to avoid accidents in the embarkment area of the cruise and ferry terminals, which has a really high number of passengers, which is 2 million passengers per year. So in this case, the tackling was about pedestrian traffic light violation, fallen cyclist in the intersection, and pavement deformation. Going forward, the devices and IoT components of the Italian pilot site, as you can see from the slide, is listed right here. We have pilot IoT sensors based on both 6-LoWPAN and narrowband IoT technologies, pothole detection. We're working on a smart trailer to announce the roadway works while passing, where we have RSUs, OBUs both on cars and bicycles, the smart traffic light, which is operated by ISMB, and the smart camera. For the network part, we use port wireless backbone, the highway backbone, and which uses the Tuscanian institutional cable network, LCG5, as stated previously by Paolo Pagano, and of course narrowband and 6-LoWPAN networks. The platforms which are used for the pass-through of information are, of course, the 1M2M platform on the cloud and the in-vehicle IoT information. This is an example of an interface that we're working on, which is the administration interface for the reliability and validation of DNM messages, which are passed through by devices and the 1M2M, because while using the DataX2 standard protocol, the message and the actual event and situation must be validated by a human, which is part of the TCC, which means that an event is geolocalized and put on the map, and this event is then validated by the TCC members sending someone to actually check for the event to be truthy or falsy. If the event is truthy, it is checked to be truth, and if true, it is accepted and sent to the other devices which spread the message. If not, the DNM is not validated and will be eliminated, also logged. As you can see, the IoT final user services would be Monica, and in our case for the CCC, the administration interface for the DNM, which would enable the port monitoring by IoT functions for drivers and VRUs. putting safety in the first spot, and the validation of IoT detections with DATEX format with events flowing through the TCC. And that would be all. Thank you very much. Let's see.
I think the next speaker is Paulo Columbo from Telecom Italia, who will introduce you about the 1M2M platform. Paulo, are you there? Paulo does not show up. We can try.
Okay, do you hear me?
Paulo, are you there?
Yes, I'm here. Do you hear me?
Yes, I can.
Yes.
Unfortunately, you are not listed among the experts, but I can show the slides if you like.
Okay.
Those you circulated a few days ago, if they are the last ones.
They are still valid.
Okay, good. If Cecilia, can you let me be presenter again? Okay, good. So this is your presentation, Paolo. If you can describe the slides by yourself.
Okay, this is good morning. I'm Paulo Columbo. I'm working on ICON one machine-to-machine platform. So this is an overview, a general overview. You can move directly to the slide 4. Okay, I presented here a very short overview of one machine-to-machine. So the main point is the team provides an instance of ICON that is a store and share platform compliant with the one machine-to-machine standard. But what is one machine-to-machine standard? So the name is easy to understand. It's a standard for machine-to-machine, but in general, one machine-to-machine is a global organization that defines a lot of things about one machine-to-machine. For example, requirements, architecture, API specification, security solution, interoperability for one machine-to-machine and IoT technologies. So I mean all the things that are useful for this matter. So the main features supported by one machine-to-machine standard are a software and middleware layer, a common set of functions to application via API, data stores and share, access control, and notification about events to application. So the point is that a platform compliant with one machine-to-machine standard is a platform of store and share, and these are the main point of the standard. In the following slide, please, you can move to the next one. Okay, in the following one, there are the standard defines two entities that are the application entity and common service entity. What is an application entity? Is a source that produces data or that reads data. So for example, in this case of AUTOPILOT project, a source may be an OBU on a car, or an application may be a cloud application or an Apple smartphone that uses the data stored on the platform. ICON is the second type of entity that is a common service entity, CSE, and this platform provides a set of functions, for example, data management and repository, subscription and notification on events, registration, security, and so on. The interface between these two entities, between application entity and common service entity, is called MCA reference point. In this very simple picture is described the two link between the platform and, for example, the cars, and with the application, for example, a smartphone. Okay, next one. Okay. What is, like I told before, ICON platform is a platform compliant with the standard. And the team provides this platform as a platform as a service. That is a cloud model that provides all the infrastructure required to create and manage custom cloud applications. ICON is installed in a team self-data center that is a commercial platform for hosting managed directly by team. So this is a platform that is exposed directly on public internet at this link. The original product is based on open source product that is named Ocean, and this product by a Korean consortium. Okay, in this slide are reported the main features of ICON platform. That is, of course, the compliance, the presence of southbound and northbound REST APIs for data storage and sharing, the data sharing by means of pull and push. Each resource is identified by an URI. There are a web access console for both for resource management and provisioning, or also for administrator. Is service independent, so there is an interworking also with the legacy platform and one machine-to-machine platforms by means of a layer of adaptation. Of course, this platform is multi-tenancy, so a lot of tenancy can use this platform, and each tenant can see only the area reserved to his tenant. Okay, next one. About security aspects of the platform. These are reported the main features that use the APIs are exposed through SSL, both for HTTPS or MQTT protocol. The authorization is based on credential and associated with a specific user. For example, AUTOPILOT project has a specific tenant, of course, with a specific credential. Last but not least, there is defined also by the standard one machine to machine an access control policy, ACP, that needs to be created for each application entity. In other words, an access control policy defined as a set of conditions that determine whether entities are permitted to access a protected resource. This is a high-level architecture. In the center, of course, there is the platform, the ICON platform. In the lower part of the picture, there are the source of data that can be or entity one machine to machine compliant, or other sources via gateway or legacy IoT platform that are not one to machine to machine. So there is, as you can see, an there are the adapter, an adaptation layer that converts the other protocol in one machine to machine protocol. Also used in AUTOPILOT. Thank you. Also used in AUTOPILOT project, there are also a core narrowband IoT. So there are a source of data that are transported by mobile network, in particular via narrowband IoT. Of course, in the upper section in the upper part of the picture, there are applications that access to data stored on the platform, also via REST one machine-to-machine API. Okay. Okay, this is a resource tree. The resource tree is the data structure that ICON and one machine-to-machine standard uses to store data. As I said before, there is a tenant called AUTOPILOT, and this is a container that in this tenant there are groups of container divided on the type of data. For example, I highlight the part about the RSU. And there is a container that store CAM messages from a vehicle. And for each vehicle, there is a container. The container is a basic element of for the storing data. In the next slide, we can see the content instance. The meaning is the data that are stored for in each container. For example, about the example of a CAM message, you can see for CAM vehicle number 3902, there are a lot of content instance. For each instance, there is a CAM message store. In the upper part, there are attributes and values defined and added by the platform, and the lower part, there are the content that is a CAM message. Okay, this is the last slide, and are only described the interface supported by one machine-to-machine platform that I mentioned also before, and that are HTTP, MQTT, that is the classical protocol, web protocol, and also MQTT and COAP, that is a protocol for low power for devices with low capacity about consumption. And so it's the protocol very light, used often in the machine-to-machine world. As I told before, also there is an adaptation layer that is fundamental to convert a non-one machine-to-machine protocol with a standard protocol supported by ICON. Thank you.
Thank you, Paolo. So I think after having described the 1M2M platform, it's now time to describe what the autonomous driven vehicles are publishing on this platform and how can they consume information coming from the IoT. So next presenter is from FCA Group, Centro Ricerche Fiat, engineer Leandro Dorazio. Can you, Leandro, are you there?
Thanks, Paolo.
Okay.
Yes, I'm here. Okay. Okay, so good afternoon, everyone. As Paolo said, my name is Leandro Dorazio. I'm working with FCA CRF. So in this presentation, I give you a brief overview of technical features which have been implemented in the prototypes of the Italian pilot site. And I try also to give you an idea on how IoT information is used for automated driving maneuvers. So the presentation will be organized exactly to describe this content. So the first part is aimed at describing the architecture of the prototypes of the Italian pilot site, both from a software and another point of view. And the second part is aimed at understanding how IoT information can be used to improve automated driving maneuvers and to provide a better user experience to the driver and a safer experience. So let's start with the first part. Okay, so here you can see the high-level architecture of the vehicles which are used in our pilot site. So now, without entering into details, you can see that there is a part which is dedicated to communication devices. So all this part is aimed at communicating with the external world. So through to communicate with other vehicles, which are also connected, there is a unit, the cloud, and so on. Then, of course, this link is also used to, to receive IoT information from outside the vehicle and to use it inside the vehicle to perform automated maneuvers. Then, okay, here you can see all the sensing devices which are embedded in the vehicle. So the idea of these devices is to understand how the vehicle is performing on the road and also to detect potential obstacle in front of the vehicle and in general to understand the surrounding environment the vehicle can find on its own path. These two information sources are then used by the vehicle itself in order to understand which is the best maneuver to be performed in an automatic way, of course. And the same unit is also aimed at informing the driver through the HMI on the vehicle for possible, let's say, dangerous situation or any external event that need to be, let's say, seen by the driver. Now, if we go a little bit deeper into details, you can see here the software architecture which characterize the Italian prototypes. So here, of course, I'm not going into details, but it is just to give you an overview of the complexity of the software architecture that has been embedded on our vehicles. Now, okay, here you can see some components that have been already discussed before. And as you can see, each, let's say, macro component is, is characterized by more subcomponents that are used to implement for specific functionalities for each module. Of course, in the design phase, we had to identify and to define the interfaces among all these components, because you can understand it was not so easy to have such a huge complexity on a single vehicle, and so we need to carefully design every detail of the architecture. So this is from a software point of view. Of course, the full architecture is not implemented on a single device, on a single hardware device, but it is distributed over different devices of the car. So here, for example, you can see the hardware architecture of the connected and the automated driving vehicle. Now, just to give a brief overview, as you can see here, we used two dedicated CAN buses to share information among the additional devices which have been required by the AUTOPILOT architecture. Then, of course, we also have the connection to the original CAN bus of the vehicle, which is used to, let's say, to actuate the maneuvers that have been decided by the central AD unit of the vehicle. So this AD unit, as I said before, uses the information coming from the in-vehicle sensor, like, for example, the frontal sensor, but also from the outside of the vehicle, like, for example, the IoT information coming from the external world, or the information about the horizon, which is also fed by external information. And of course, at the end, you also have the HMI, which is used to warn the driver and to provide information in general to the driver. So this is the architecture, the hardware architecture of the connected and automated driving vehicle. And we also identified a dedicated architecture for the connected vehicle. As you can see, the connected vehicle is, let's say less complex, but of course is still important for our use cases, because it provides information both to the cloud, and is also able to receive information from the cloud in order to always warn the driver about possible dangerous situation. So now this is a brief overview about the architecture. In the second part of the presentation, I'll give you an overview on how IoT information is used by our vehicles. So here you can see, let's say, a breakdown of the AD unit of our vehicle in terms of, from a software point of view. So as you can see, the AD unit, which before was represented by a single system, can be divided in three different modules: a perception module, a manual module, and a control module. The perception module receives the information from the sensor which are embedded on the car, and from the information which are coming from the external IoT. So as you can see, all this information together is fused in order to feed the maneuver module, which decides the best maneuver for the vehicle. And then once the maneuver has been decided, let's say, this information is passed to the control module, which actuates the real motion of the vehicle, both in terms of lateral and longitudinal control. Now, just to give you some more details about which kind of information we are talking about, here you can see a detailed breakdown of the information which are coming from outside the vehicle and from some of the sensors which are embedded in the vehicle. Now, if the perception module is able to fuse all this information and to provide as output a description of the scenario which can be used to understand which kind of maneuvers the vehicle has to perform. So once the scenario has been clearly described by the perception module, the maneuver module is then able to decide which is the best maneuver to be performed, and then this maneuver is passed to the vehicle for the final actuation. Okay, so this is just to give you a brief overview of the information we are talking about. Now, just one last slide to recap what can we do with this architecture. So without entering into details, because Lorenzo already presented some of the use cases which we are implementing on our pilot site. But here you can see that all the information which has been described so far, the one M2M platform together with the cloud, the sensor on the road, the vehicle itself, can give us the possibility to use IoT information coming from the external world in order to feed automated driving maneuvers and to perform specific use cases that otherwise couldn't be implemented on this kind of vehicles. And okay, so this is my last slide. Thanks for your attention.
Okay, thank you, Leandro. I think we move to the last presentation before the questions and answers session. I give the floor to Daniele Brevi from Istituto Superiore Mario Boella from Turin. Daniele,
Okay,
the floor is yours.
Thank you very much. Can you see my screen?
Yes, we can.
Okay, so thank you. My name is Daniele Brevi. I work for Istituto Superiore Mario Boella, that is a private research center based in Italy. And today I want to present you how we use IoT to implement the urban use cases of the Italian pilot site. So first of all, we think that IoT is the base to enable local awareness, and then IoT and local computation can bring high benefits to automated maneuvers. This is really true for safety-related services because they typically need very low delays, both considering computation and transmission point of view, but also to enable others high-value services. These are typically based on local information. And then we also have other type of services, typically non real time, that will benefit of the data that we are saving on the IoT platform, that is the one M2M platform described by Paulo. So this is a brief overview of our architecture for both the IoT onboard unit and the IoT roadside unit. So as you can see, the base are the IoT devices, and we are using basically inertial sensor, both on car and on a bicycle. We will see in a while how. And for the roadside point of view, we are using a stereo camera to perform the pedestrian detection and a traffic light to read its phases and to send them to the vehicles. Then we have the computation level. From the roadside unit point of view, we have the management of the IoT pedestrian detection, and then we have a module to send a notification to the vehicle based on this detection, and also to send SPAT messages. All these data are sent over the G5 communication channel and are received by the onboard unit of the car, but also by the onboard unit of the bicycle. And there on the onboard unit, we have the computation, so the fog computation, the one very near to the real devices, where we have the module to manage the virtual photon sensor, and then we have another module to filter relevant data. We will see in a while how. Okay, so we have several actors in the urban use cases. So I will describe you one by one, and the first is the IoT in-vehicle platform. Here, as I said, we manage all the messages. The one from HG5, the messages sent via LTE to the one M2M platform, but also we collect data from the accelerometers using different channels like Wi-Fi or 6LoWPAN. And then we also perform fog computation. So we filter all the information and we send them to the D function only when relevant. So for example, if we are too far from the traffic light, we filter the sending of information to the AD function. And also if we are not in the direction of the traffic light, so we are, for example, only nearby the traffic light, but we will not pass towards it, we will filter this information. And then we will also aggregate and analyze accelerometers to create a virtual sensor view. But I will describe this later in more detail. Then we have the smart traffic light with the pedestrian detection module. So here you can see a picture done in Livorno during our experimentation. So we have the roadside unit, a stereo camera for the pedestrian detection, and the Wi-Fi connectivity provided by CNIT to connect to the 1M2M platform. And here you can see a picture of our hardware. So we have the GPS and the CG5 module, the traffic light that is connected with a normal USB connection, and then the CPU and GPU that are used to manage the camera. So the main function of the smart traffic light is for sure the pedestrian detection. And here we have used a well-known algorithm called the histogram of oriented gradients that it's quite famous. And it is also included in the well-known OpenCV library. So the limitation that we have found in the first experimentation with this type of algorithm are the following. So it is computationally expensive. So for this reason, we need a GPU to work in real time. Otherwise, we cannot detect and send information in time to the autonomous vehicle. And we find also that there are many variables that can change the performance of this algorithm also in a significant manner. So it's quite difficult to generalize it for every situation. Also, abstraction can be a problem. So it's not too easy to find the best point of view. And here we have to find also a trade-off between false positive and false negative. So let's see what this means. So for example, in this first picture, we have 1 true positive and 2 false negatives. So this is quite a dangerous situation because, for example, if the first pedestrian goes very fast, I have the last 2 pedestrians that are not detected by our algorithm. So in this case, I can have a situation, a dangerous situation where the automated maneuvers cannot see the pedestrian. But if I change my parameters in order to have less false negative, I can have more false positive. So as you can see here, the light conditions are not so good. So the algorithm takes a net for a pedestrian. So in this case, it cannot be so dangerous as a situation, but I can have a problem of comfort because, for example, if the detection is flickering, I can have the car that is braking and accelerating and then braking and accelerating. So this is it's a problem of very discomfort for the user. So the last picture is the one that we want to have, but that it's not possible to have all the time. So finally, it's a problem about safety versus comfort. So we have to manage all these things. So the extensions that are under development are, first of all, try to change the algorithm. So image processing activities are going very fast in these years. So we have find some new algorithm that seems better than the one that we have used since now. And then thanks to the stereo camera, we can also measure the distances. So we can try to understand better where the position of the pedestrian is. So here we have to understand how much accuracy we can achieve. For example, if we can have a lane level accuracy or more. This because our final goal is to do pedestrian tracking. And so here we have to understand what about computation requirements. So if a GPU is enough to do all the things that you want to do, for example, where we have 4 or 5 people crossing a street. And then we have also to understand if we need non-standard messages to send all these information to the autonomous vehicle. Okay, the third one is the connected bicycle. Here, the use cases is the fallen bicycle. So we want to detect if the bicycle is falling and then send the messages to the car. As you can see, here we have another type of IoT platform. This because in this case, we need to power this platform with a battery. So we need something a little bit with less consumption than the onboard unit that we have on the vehicle. And here, in order to understand if the bicycle is fallen, we use an inertial measurement units integrated in a GPS, and we use the raw values of its accelerometers to detect the fall. And then, thank you to the HCG5 module, we can trigger the sending of a DNM message. And it's also important to say that our bicycle can also send CAM messages exactly as a vehicle. And here we have chosen the inertial unit also because in this way we can feed the fields about the vehicle dynamic. That in this case is not a vehicle, but is a bicycle. Okay, the last components is the pothole detector. So here we have tried to use a virtual sensor concept. So we all know that today all the vehicles are increasingly equipped with different type of sensor, and we think that combining data from different sensor or from different sensor, but of the same type, we can improve the accuracy and the reliability of sensor data, but we can also create a sensor that bridge what can be measured from to what developer want to detect, leveraging sensor fusion techniques. So our virtual pothole sensor, it's composed by 3 different accelerometers. So one using the accelerometer that are inside a smartphone, and that can be sent, the information can be sent via Wi-Fi. The second one is a vibration sensor that exchange data using the 6LoWPAN channel, and this is provided by CNIT. And then the third one is inertial measurement unit provided by CRF. So the current implementation of the algorithm is based only on the smartphone data, but we are working to integrate also the other 2 sensors. And here you can see how it works. So we have the 3 different sensors, the data are combined and sent through MQTT to our IoT onboard unit. Here you can see some example of real data collected on field during the last campaign in Livorno. Then, thank you to this data, we can understand if there is a pothole, and so we are sending this information to the 1M2M platform in a crowdsourced way, so their services can use in a smart way this data, for example, sending notification to other vehicles in that area in order to let them avoid possible pothole. So here you can see the team that has developed all the things that I have described. And so thank you very much for your attention.
Thank you, Daniele. So now I open the floor to questions and answers. Please use the chat box to send questions to the experts that who have presented their slides. Is there any question from the audience? Okay, I have a question actually, so in order to let you not to be shy, I start first, and Leandro, from the perspective of the car maker, in the, how to say, general strategy of the car makers, what is the Autopilot project providing you? Which kind of perception of the state of the art, the interest of gathering information from an IoT platform, the real, how to say, extension of the electronic horizon of the vehicle. How can this, how to say, new inputs are considered by the car makers?
Okay, thanks, Paolo, for the question. I'll try to give you a general answer, and not, of course, based on the FCA strategy, of course. So, from our point of view as car maker, the idea of having information coming from outside, from IoT, from the cloud, and so on, is of course of interest for us. But because it gives us the possibility to, how to say, to enhance the perception of the vehicle, and to expand also the safety limit of the vehicle itself. Because thanks to the communication, of course, we are able to extend the range of in-vehicle sensors that usually are limited to a few hundreds of meters in that case. But on the other side, we need to be careful about using information coming from the communication, because for, as you know better than me, each, let's say, telecommunication system cannot be validated from a safety point of view. In particular, if we talk about functional safety, any system that is based on just communication cannot be, let's say, certified in an easy way. And that is the reason why usually we try to, let's say, to fuse the information coming from outside with the information which is available, which is already available in the vehicle. So the target, from my point of view, is the data fusion of information coming from outside and the information acquired by vehicle sensors.
Thank you very much. And another question is if is there any? There is one raised from Giovanna Larini. Okay. So Giovanna, can you ask me question or to anybody? Giovanna? Giovanna, did you raise the arm for asking questions? Okay, so I try to go ahead, ask another question to Lorenzo Pieri, if he's still there. Lorenzo, are you there?
Yes, I'm still here.
Yeah, what is the benefit of including the DATEX node into the control loop of this cooperative extended IoT-based cooperative ITS?
Well, thank you very much for the question, Paolo, and I will answer gladly. As I have said previously, the DATEX2 is European standard for the roads, for the highways, and it is a well-known and used standard in this cooperative environment, which means that the possibilities are really big, and there are already a lot of experts that can work side by side in this kind of environment, bringing forth the state of the art that this research is looking for. So I think DATEX2 protocol, which is highly standardized and also went under renovation just a few weeks ago, is really the go-to protocol for this kind of cooperative environment with the exchange of road informations. Thank you.
Actually, I say myself a remark on this new feature of the AUTOPILOT test site in Italy, that of extending the scope of the traffic control center to the cooperative ITS permits a pervasive capability of detecting events. And so events are not reported by humans by calling the control center itself, but machine to machine by the devices. This is some good insight into the IoT realm, into the IoT challenge, and especially in the domain of intelligent transport system, this will provide a real, to say, good feature of feeling the perception of events that are happening in real time, far from our from the capabilities of sensing of board devices, and also from the capabilities of fog communication, let's say medium access layer communication that is provided by HCG5. Okay, I don't know whether are there other questions. I ask Cecilia to help me. How much does this Q&A session last?
Hi, hello. Unfortunately, no, we don't have any other questions. So I think we can close the webinar and thank all the participants for attending.
Yeah, my only final remark is that a two-day event is approaching now in Livorno. There will be a dedicated day for stakeholders for exploiting the results of the project on October 18. And there will be a public demonstration of the technologies we have developed so far the day after, on the 19th. So if you are interested into these topics, please drop me an email and I will reply. Thank you so much for your participation.